Hi everyone. This lesson is about exponential probability distributions. Now, got a little bit of information here. That is the function for an exponential probability distribution. It's a piecewise function. We only allow values of x which are larger than 0, and lambda is a positive constant. So it says it up there, lambda has to be more than 0. And that gives us a graph that looks a bit like this. Now, before we get any further, let's just have a little look at what that looks like. So this is my lambda value greater than 0, and that's the exponential function. Now, as you might expect, for a probability density function, all of those values have to be above 0, which they are, and the total area has to equal 1 if I integrate. Now, I integrate it to 200 just because I set the maximum domain at 200, but it's rounded off close enough to 1. As I change the value of lambda, if I increase lambda to 2.5, there's a couple of things happen. The starting point increases to 2.5. The graph has to be a little bit steeper in the way it drops because we have power of negative 2.5 here, but we still end up with the total area equal to 1. It's still a probability density function. Lambda can be all the way down to, but not equal to 0. If I put it 0, it just flattens off. So lambda has to be more than 0. And that's our exponential. It's a perfectly good probability function. Now, as you might expect, you could find a cumulative density function by taking the integral of this function between 0 and x. And if you do that, you end up getting a graph that looks like this. As you would expect, as you go to larger and larger values, the probability gets closer and closer to 1. As I change the original function, the cumulative function still starts from 0 and maxes out at 1. It just rises more steeply if I have a larger value for lambda, or it rises more slowly with smaller values for lambda. Now let's go back to the notes. As you know from your studies in maths methods, you can calculate the expected value of a density function with this rule, and you can calculate the variance with this rule, and from that the standard deviation. Now, if you're interested in the details, I've attached a couple of documents into our OneNote here that I'll share with you, that you can see the working for those. That's not really the point of today. If you do all of that working, it turns out that the expected value and the standard deviation of one of these probability functions is 1 over lambda. So lambda is an important number. Now, let's have a look at how we might do some questions. We have here a time t minutes that it takes for the librarian to locate a book is an exponential distribution with a mean of 3 minutes. Let's see if I can get my pen to work here. Okay, wish me luck. So if the expected value of the random variable is 3, then we can say from above that that's 1 divided by lambda. In other words, lambda is 1 over 3. Then the density function, so the probability function, it would be a piecewise function with lambda times e to the power negative lambda times x, and that's if x is larger than or equal to 0, and the value of the probability is 0 when x is less than 0. So that's part A. For part B, find the probability that it takes the librarian less than 2 minutes to find the book. So as we've seen, we would have a graph that looks a little bit like this. That should have been a solid dot, it's included. That's my probability density. That's my value of x. And we're looking for a time less than 2 minutes. So we want to find the area between 0 and 2. So the probability that x is less than 2 is the definite integral between 0 and 2 of the function 1/3 e to the negative 1/3 x dx. Now, you could do the integration algebraically, or we could solve it here on our calculator. So we've got, actually, just go back here. I've tried to set this up already. So I could set 1/3 as the value of my parameter L, and then change that to be from 0 to 2. So it's just going to put 1/3 in here, and that gives me 0.48, 0.49 if I round off. So there's my probability, 0.49. There's about a 49% chance that the book is found in less than 2 minutes. And that's a typical sort of a question that you might have for one of these topics. Here's another one. Customers at a checkout wait on average 6 minutes to be served. So that tells me that the expected value of this function is 6. And from that, we can write down that lambda is 1 on 6. Now, write down the function. I won't do part B because that's about the same as the other, but I will do part C. So the function would be p of x, it's a piecewise function. It will be 1/6 e to the negative 1/6 x, and that is when x is greater than or equal to 0, or it would be 0 when x is less than 0. Now I'll skip part B and I'll do part C. Find the probability that a customer waits more than 10 minutes to be served, given they have already waited 5 minutes. Let's just draw ourselves a little graph. So they've already waited 5 minutes. And what's the chance that they have to wait more than 10 minutes and they've already waited? We know they've already waited 5 minutes. So this is using a little bit of prior knowledge. This is conditional probability. This is the probability that the time is greater than 10 minutes on the condition that the time is already greater than 5 minutes. Now, using our rules, that would be the probability that time is greater than 10 intersect with time greater than 5 over the probability that time is greater than 5. Now, the intersection of those two is just the black shaded area. So that would be the integral from 10 to infinity of my function. It was 1 on 6, wasn't it? 1 on 6 e to the negative 1 on 6 x dx. And the probability greater than 5 is from 5 to infinity. Integral from 5 to infinity, 1 on 6 e to the negative 1 on 6x dx. Now again, we could do those algebraically. We'd have to use limits as we approached infinity, or we could approximate this on our calculator. So let's just go back to this one, and we'll make our lambda constant 6, 1 on 6. Then I've got to be a little bit tricky here. So my lower limit is going to be 10, and my upper limit is supposed to be infinity. Well, I can't type infinity, but I can type a large number like 1,000. And so the value of the integral on top is 0.1888. And we do the same thing for the denominator with a lower bound of 5. So we have 0.4346. And then finally, we've got about a 0.43 percentage chance, 0.43. So that tells me that if you've already waited 5 minutes, there's about a 43% chance that you'll have to wait longer than 10 minutes. So that's a slightly more complicated one because we were using conditional probability with that density function. Okay, that's enough. Thanks for watching.